Welcome to Lesson 2 of Module 3, on the concept of convolution. Today, we will cover how convolution works, as well as the techniques of stride and padding. We will then discuss some convolution examples. Convolution is a mathematical operation that involves sliding a small matrix, called a kernel or filter, over a larger input matrix and computing a dot product at each position. The resulting output matrix, which is also 2D, represents the spatial relationship between the input elements and the filter weights. The output value at each position is a function of the values in the input matrix and the filter weights. This process is widely used in image and signal processing for operations such as feature detection, edge detection, and blurring, as it excels at detecting structures within the data. The size and shape of the kernel or filter play a crucial role in the convolution process. Different filters can emphasize different aspects of the input data. Larger kernels generally provide more global information, capturing broader patterns and structures, while smaller kernels focus on local details and fine-grained features. To calculate the 2D convolution, use the kernel and slide it over the input image. Multiply each element in the input with the corresponding position in the kernel, and then sum up the terms. This is called a dot product operation. The kernel moves to the second position. Now apply the dot product to the next inputs with the corresponding position in the kernel to create the second output value. The kernel moves down to calculate the third output value. Finally, the last element is computed from the final position of the kernel. In image processing, stride refers to the step size that is used when applying a convolutional filter to an input image. Specifically, stride is the number of pixels that the filter is moved horizontally and vertically across the image when performing the convolution. A larger stride value means that the filter skips more pixels when moving across the image, which results in a smaller output size. Conversely, a smaller stride value means that the filter moves more slowly across the image, which results in a larger output size. Stride is an important parameter to consider when building deep learning models for image processing. Increasing the stride can reduce the computational complexity of the network and speed up the training process, but it can lead to a loss of information if important features are skipped. Decreasing the stride can improve the accuracy of the model by allowing it to capture more fine-grained details, but it also increases the computational cost and might lead to overfitting. Overall, choose the stride value based on the specific requirements of the problem and the available computational resources. In general, a smaller stride value is better for tasks that require high accuracy and fine-grained feature detection, while a larger stride value is better for tasks that require fast computation and coarse feature detection. Here is the mathematical formula to calculate the output shape given the height and width strides, SH and SW respectively. In image processing, padding refers to the process of adding extra pixels to the edges of an image before applying a convolutional operation to it. Padding is used to preserve the spatial dimensions of the input image after the convolutional operation, and it's an important technique in deep learning and AI. When a convolutional filter is applied to an image, the edges of the image are not processed in the same way as the central pixels. This can lead to a reduction in the size of the output image after the convolution, which can be problematic when trying to build deep networks with multiple layers of convolutions. Padding addresses this issue by adding extra pixels to the edges of the image, which ensures that the edge pixels are processed in the same way as the central pixels. Padding can be done in different ways, such as adding zeros or replicating the edge pixels, and the amount of padding can vary depending on the size of the filter and the desired output dimensions. By using padding, it's possible to preserve the spatial dimensions of the input image, which can lead to better performance in image classification, object detection, and other computer vision tasks. Here is the mathematical formula to calculate the output shape given the amount of padding in the height and width dimensions, pH and pW, respectively. Note that the padding specified here is the total padding per dimension. However, PyTorch framework requires padding to be specified as the amount added to a single side for each dimension. A 1x1 convolutional layer, also known as a pointwise convolution, is a type of convolutional layer that is used in deep learning models for image processing and other applications. Unlike traditional convolutional layers, which use square or rectangular filters to scan the input image, a 1x1 convolutional layer uses a 1x1 filter, which only considers individual pixels in the image. Specifically, the filter is applied to each pixel in the input tensor independently. This results in a new tensor with the same spatial dimensions as the input but a different number of channels. The reduction in number of channels is a consequence of the dot product between the image matrices and the kernel over multiple channels. One common application of 1x1 convolutional layers is in the design of network architectures, where they are used to reduce the number of channels and reduce computational complexity. For example, a 1x1 convolutional layer can be inserted between two larger convolutional layers to reduce the number of channels before the next convolution, without changing the spatial dimensions of the data. You can also apply convolution to color images. In that case, you can use different kernels for each color channel of the image. A convolutional neural network, CNN, is a combination of the convolution technique and some additional methods that help identify patterns. More details will be covered in the next lesson. In the next lesson, we will cover convolutional neural networks, as well as how to use PyTorch to build a CNN. Thank you.